Hello, am I audible?
Yes, sir.
So, in the previous class, we discussed about the SR and JK flip-flop. Now, in this class, we start with the D flip-flop. Okay, so first of all, what is D flip-flop? Then D latch. Okay, so basically, we start with the D flip-flop. So that is the third type of flip-flop. Okay, so basically, it is called the, as I already told, this is the called the delay flip-flop. Okay. So, D flip-flop is the- okay. Delay. Okay. Like for example, in the programming part, I think in the basically embedded C or some programming part, you require some delay part. Delay. Okay, you require some delay. So that particular delay will be provided by the D. Okay. So this flip flop will store the data for a certain amount of time. Like I'm saying, this is my clock pulse. So when I provide the clock, okay, when I provide the clock, so after applying the clock, so we consider the clock is one. So when D and Q.
Sir, your screen is not visible.
Yes, sir. Not visible.
I'm going to share it. Now it is visible.
Yes, sir.
Okay. So now if we provide the D, we are getting output as a Qn and Qn bar. So when D is 0, Qn plus 1 is 0. When Qn plus 1 bar is 1. When D is 1, Qn is 1 or Qn bar is 0. Okay. Now it doesn't depend on what is the previous out. What is the previous output. So if we draw the excitation table for that one, okay, if we draw the excitation table, so what it says when D and Qn, D is 0, Qn 0, D is 0, Qn 1, then D is 1, Qn is 0, and D is 1, Qn is 1. Now what about the Qn plus 1? And Qn plus 1. So if you are talking about the Qn plus 1, so if D is 0, doesn't mean what is the output of previous time. Okay, Qn. If Qn is 0, 0. If Qn is 1, again 0. Why? Because D is 0. Similarly, when D is 1, doesn't mean Qn is 0, 1, and when Qn is 1, similarly Qn bar is, it is just reverse of that. Okay. Now if we draw the characteristic table for respect to this one, so characteristics table where we are considering the Qn and Qn plus 1 and with respect to 0, 0, 0, 1, 1, 0, and 1. So if you are talking about the 0, 0, so D is 0. If you are talking about the 0, 1, so Qn is 0 and Qn plus 1. When we are talking about that Q1 is 1 and D is Q1 plus 1 is 0, and when both are 1, okay, so we can directly represent as that D is nothing but Qn plus 1. So if Qn is 0, Qn plus 1 is 0, D is 0. Qn plus 1 is 1, D is 1. Okay, now if with respect to clock, I represent my data, like for example, this is my till now we are not discussing any clock diagram or timing diagram. Now if this is the clock, okay. Now we consider the clock is the positive edge. If we represent the clock as a negative edge, we use one bubble here. Okay, we use one bubble here. So what is the meaning of this one? This bubble is that this particular flip flop will be working on a negative edge. Now here, if no bubbles, that means it will be working on a positive edge. Okay. Any doubt? Just any doubt? So now, with respect to this one, I am taking the data. So maybe in my data is anything. Like for example, if I consider my data is both, just consider this. Understand this is my. Okay. Now with respect to Q n plus 1. So where my data will be changed? The data will be changed at this point. The data will be changed at this point. And the data will be changed at this point. Okay. So when clock pulse is not applied, it doesn't mean what is my Qn plus 1. What is my Qn plus 1? So I'm not considering this data. Because at this point, till this point, data is not applied. Okay, data is not applied. Now, if we are saying at this point, like for example, I just draw that. Okay, so the data here is like for example, A data is here. Okay, data A is here. So when data A is transmitting, so this particular data will be transmitted till this. Okay, why? Because only changes will be appear at this. Only changes will be appear at this. So data A will be transmitted. Now, if you see when this second clock pulse is applied, data B will be transmitted. So from after that one, the data B. Okay, and when third clock pulse is applied, data C will be transmitted. From here, data C. Okay. Now in this duration, the data will be C, but it will not transmitted at all. It will not transmit it at a output. So we can say for data C, it is a delay. Okay, it is a delay. Why? Because you apply the data C from this point. You apply the data C from this point, but it will be appear at a output at this point. Similarly, you apply data B at this point, but it will be applied at the output from this point. So this is also a delay. This is also a delay. Okay. Yes, any doubt? Yes or no? Is it clear? Any doubt?
Yes, sir. Clear.
Now, if you are talking about like I can implement this particularly delay for any point, like for example, we are saying that we provide one two inputs A and B. Okay. Now, after applying the A and B, like this particular NAND gate will be taking the 5 nanoseconds. Okay. So that is basically the internal part of the AND gate. But this 5 nanosecond delay signal, that particularly if we provide a signal at a 0 nanosecond here and 0 nanosecond here, it will be received at a output point at after 5 nanoseconds. Okay. But it will be go to other XOR gate after 7 nanoseconds. So here the data will be applied at the 7 nanoseconds. So basically, this particularly wire will provide a 2 nanosecond. 2 nanosecond. So this is not provided by the wire. This is provided by the flip flop. So basically, there are two flip flops are available. So basically, one flip flop with 1 nanosecond, one flip flop with 1 nanosecond. So two flip flops will be available who provided 2 nanoseconds. Okay. Now, if we say the data, yeah. Now the thing is that in this particularly process, some data delays provide as well as some data will lost also. Some data will be lost also. So what is the meaning of loss? Like for example, if we have false, it's the positive edge. So this is the clock signal. Now if we consider data, so data should be like that. and so on. This is the data. Okay. Now we say that it is the A, B, C, D, E, and F data is available. Now we check at this point, at this point, and at this point. Okay. In between, before that clock pulse is applied, it doesn't consider what is the data. But after clock pulse is applied, my data should be here. So my data should be. But it will be continue till next positive. Till next positive. Okay. Now after that, till next positive wave, data C will be applied. So C will be released. Now after that, D will be applied. The next positive is applied. Consider the data F will be applied. So we are getting F, we are getting D, we are getting C, and we are getting A. So there is the loss of the data. B data is lost and P data is lost. Okay, data B and data A is lost. Clear? Coming out? Now, if we are saying that we are using a latch set, so again, in the previous class we discussed what is the difference between the latch and flip flop. The flip flop is basically the S trigger, whereas the latch is the lever trigger. Now here is the clock. We QL. The data. So this is my clock data. Now if you are going with respect to the latch, so what is my Q1 plus 1? So before this particularly there is no data will be considered. Okay. After that, when we are going with a positive, so the signal 2 will be transmitted. Signal 2 is transmitted. If this particularly signal 3 is applied before the level, signal 3 is also transmitted. Okay, signal 3 is also transmitted. And that particularly signal 1, 2, 3, 4, 5. The signal 1 is transmitted, signal 2 is transmitted, but signal 3 is not transmitted because if it will be start, no, signal 3 is also transmitted. So signal 2 is transmitted, then signal 3 is transmitted. Signal 4 is also transmitted until it transmitted till this point. Transmitted till this point. 1, 2, 3, 4, and 5 all will be transmitted. Now, if I change particularly signal in a way, like for example, I just change this signal 1 lies till this point. Okay. 2 lies for this point. Okay, and 2 for this point. This is my signal. Now, in this case, what will be happen? Signal 2 is blocked. Signal 2 is not transmitted. Why signal 2 is not transmitted? Because the signal 2 arrives after completing the positive level. After completing the positive level. So till this next positive level, signal 1 is transmitted. Till the next positive level, signal 1 is transmitted. Then signal 3 is transmitted directly. 2 will be eliminated. 2 will be eliminated. So basically signal 2 is eliminated. Signal 2 is eliminated. Okay. So what is the meaning of this particular latch? Simply if we write that if clock is 1, if clock is 1, Qn plus 1 is nothing but 80. And if clock is 0, Qn plus 1 is 2. Okay. The similarly, the previous will be 1. So if clock is 1, Qn plus 1 is D, and if clock is 0, Qn plus 1 is 0. So this is a simple for the latch. Okay, because it will be working on a just it is working on a just thing. So if we draw a circuit, we the clock is 0, so it is just similar to the previous. So Qn plus. So Qn. Okay. So I naught, and okay. When clock is 0, I0 is selected. So Qn plus 1 is Qn plus 1 is nothing but Qn plus 1. Either I can write it Qn plus 1. Okay. And when clock is 1, Qn plus 1 is equal to. Okay. Similarly, if you are using the Qn plus 1 bar, Qn plus 1 bar, so what we have to do, we are using one inverter. Okay. Here we are using the clock first. Okay. Now I0, I1. So when clock is 0, okay, and this Qn plus 1 bar is here. So here Qn plus 1. Okay. So Qn plus 1 bar is equal to Qn plus 1. Qn plus 1. Okay, Qn plus bar is equal to Qn plus 1, but it is a round. Because we see that when clock is 0, Qn plus 1 is equal to Qn plus 1. And when clock is 1, Qn plus 1 bar is equal to B. So now what should I do? I just implement here as a mod. I just implement as a not here. So if it is a D, it is a D bar. So Qn plus 1 bar is a D bar. Okay? But so second condition is solved. Now we are focusing on the first condition. So if you see that when we are getting the Qn plus 1 bar, so it becomes a Qn plus 1. So what should I do? I just take a complement. I'll just take a complement here. So it is a 2n plus 1. So now my equation is correct. So when clock is 0, we are getting a Qn plus 1 as a Qn plus 1. 1, we are getting a qn plus 1 is equal to p. Okay, qn plus 1 is going from this one, so we are getting as a qn plus 1 here. Okay, we are getting a qn plus 1 here. Okay, it becomes a qn plus 1 bar. So we are getting a here as a qn plus 1 bar. Okay, and inverting of this one is a qn plus 1. So when clock is 0, we are getting a qn plus 1 is equal to qn plus 1. Okay, and when clock is 1, so we are getting a D from here, so become D bar. Here we are getting a D. And what of this one is that D? So qn plus 1 is equal to. So there are two options you can implement either this way or this way. Okay, you can implement for both ways. Okay. Now, what is the purpose of implementing second circuit is? What is the purpose of second circuit is that this this particular inverter would also behave as a buffer. So when I'm using one inverter connected with one inverter, so that circuit is called the buffer. Okay. So if we are using a even number of inverters in a feedback path. Okay. That particularly will be used as a buffer. That particularly will be used as a buffer. What is the meaning of even number of inverter in a feedback path? I will explain. And when we are using a odd number of inverters in a feedback path, we use as a inverter. Okay, we use as a. So what is the meaning of feedback path? Like for example, if we are using this one, okay. Now in this way, you can see there are the four number of inverter we are using. Okay, so the number is even. So CERT says that if we are using the even number of inverters, so that will be viewed as a buffer, but it is not a buffer. Because you can check if you apply a 0 here, we are getting a 1 here, 0 here, 1 here, and 0 here. Okay. Now if you apply a 1, 0, 1, 0, and 1. Okay. Like for example, if you are using 1, 2, and if you apply a 0, 1, 0, now 1. So we apply 0 and we are getting a 1. We are getting a 1. So inverters. Okay. But what is the feedback path? When we start from this point, so it will be a loop. This is a loop. It's a connecting loop. So that particular loop is called the feedback. Okay, that loop is called the feedback. So always consider this particular loop. So even number of loop path has a loop path. So even number of inverters in cascade. Okay, in a cascade. Use as a buffer. And odd number of inverter in a cascade circuit. Use as a. So here we see that three particular inverters odd numbers. So when we apply the 0, it will become as a 1. When we apply a 1, it will behave as a 0. And if we are using a 4 inverters, so with the 4, when we apply 0, we are getting a 0. When we apply 1, we are getting a 1. So it will behave as a buffer. Okay, so inverter and buffer units. Now, why this particularly inverter and buffer unit is used? Why we require this particularly cascading? Only for the delay. Only for the because every gates will be having a delay. Okay, as you know that every gates will be having a delay. Now, this particularly is called the positive. If we are talking about the negative latch, so what is the definition of negative latch? Negative delatch. Any idea what is the definition of negative delatch? When clock is 0, that means negative level. We are getting as a Qn plus 1 is equal to Q. And when clock is 1, we are getting Qn plus 1 is nothing but a similar Qn plus 1. Or we consider Qn. Okay, Qn. So only the change is the sequence. If clock is 0, okay, we apply the clock, and if clock is 0, we are getting use as a Q. Okay, and when clock is 1, we are selecting Qn plus 1 as a Q. So we are selecting, or we are Qn. You are already aware about the 2 cross 1 marks. So I am using a 2 cross 1 mark. This is the I0. So Qn plus. Okay. Now, again, we have to implement this one with the help of NOT gate. So I consider this as a 1 NOT gate. Okay, I consider this as the 1 NOT gate. And if the data will be inverted, so in the output we also use the 1. Again, the output is inverted. Okay, and similarly, this data will be inverted, so we are using 1 inverted. So both will be eliminated. This effect is eliminated, and this effect will be eliminated. So both effect will be eliminated. Okay, so with the help of NOT gate, we are creating a negative latch. So this is a negative. Any doubt in this one? Does any doubt in this? Okay. Now, if we want to convert this latch into the, if we want to convert this latch into flip flop, what we do? We are cascading two latches. One is a negative D latch, and it will be cascade with positive. So after that, we are getting a level. Sorry, S. After that, we are getting a S. Okay. So we draw the waveform. Just make block signal. This is the edge level. With respect to this, I am giving the output D into D. Okay. Now first we pass through the negative latch. Okay, first we pass through the negative latch because negative latch is cascade with the positive latch. So when I'm just saying that this is the Q negative and this one is the Q positive. Okay. So what is the initial input output is the Q negative. So before this negative level, we are getting a, okay, we are getting a, after this negative level, anytime the data will be changed, so initially it will be the 1, 0. Okay. Now for the positive level, it will be again a constant, and then the negative level, it becomes a 0. Yeah. This one. Now we apply the Q positive. Now we apply Q positive. So here we are getting a 0. The negative has no changes, so if there is changes, so it is a 0. Now for the positive level, it will be getting a 1. The negative, it is again remain a 1, and so on. Okay, this is the Q negative, this is the Q positive. Now if we compare this one, this particularly Q positive. So if I say that this is the positive edge, okay. So what is the output? The data that will be appear at this point, it will be positive. So initially, if the data is 0, then 1, 1, then again 0. So can you say the data at Q positive is equal to the Q positive edge? Yes. Okay. So we can say when we cascade negative level, then positive level. When we cascade the negative level with the positive level, latches. So the behavior of these two latches will be similar to the positive edge triggered with flow. So the behavior of these two is similar to the positive edge. Okay. Now the first latch is called the master latch. And second is called the slave latch. Clear? Any doubt? Yes, any doubt? Student, any doubts? You can ask.
No, sir.
Now we are going with the
Can we solve PPS?
which one?
Practice assignment.
Okay. Just one.
In week 9, there is no practice assignment, but we can solve similar type of questions.
Wait a minute, I will check. Just give me a minute. Week 9. Week 9. There is a practice assignment. Yes. Please check on your screen that it is a practice assignment is available or not.
No, sir. Practice assignment is not available, but
Can you
We
refresh
can
it?
solve similar type of questions, sir. Like
Can you refresh it? Can you refresh your screen basically and just check? Please refresh your screen and then check.
yes, sir. Now available.
Share my screen. Yes. So there is particularly one figure is given for a common data question, that is from figure 1, question 1 to 8. Now the question number 1 is the circuit shown in the figure is. So if you see, this is the first circuit where we are connecting a D as a 1 with a negative clock. Okay, and the output will be the 1 at a positive clock. Okay, so if you remember our circuit is this one. Okay, our circuit is this one for the negative latch. Can I interchange I0 and I1 and use clock in place of clock? I can use the clock bar. Yes, in this circuit, if I interchange the I0 and I1 and replace this clock as a clock bar, so any effect on the output?
Yes, sir.
When clock is 0, which one is selected? I0. Okay, or so we can say that Qn plus 1 is B. Yes. Let's explain it. Like for example, which is our negative latches I0, I1. Okay, now if we are using the clock, so when clock is 0, okay, when clock is 0, what is the Qn plus 1? Yes, when clock is 0, what is the Qn plus 1?
T, sir.
When I apply the clock is 0, what is the output? Simply it is a 2 cross 1 mux.
I think no change, sir.
Hmm? When clock
No
is
change.
0, D is I0 is as a output. Hmm? Yes, when clock is 0, I0 is as a output. And when clock is 1, I1 as a output because it is a 2 plus 1 mux. Yes, 2 cross 1 mux. Any doubt? No? Now what is I0? So when we apply a D, it become a D bar. So we are getting a D bar here. With the D bar, it is a inverted. So we are getting a D here. So it becomes a D. It becomes a D. And when clock is 1, so Qn plus 1, that will be go in the backside. So it is a Qn plus 1 bar. Now it will be going outside. So here we are getting a Qn plus 1 bar. Now Qn plus 1 bar apply on an inverter. So we are getting a Qn plus 1 again. Okay. And this property will be shown by the negative edge. Now what should I do? If I, in place of clock, I use as a clock bar. Okay. In place of I1, I use the I0. So, okay. And in place of I1, we use the I0. What is I0? Now, when clock is 0, or we can say the clock bar is 0. So that means clock is 1. Okay. So what is the Qn plus 1? When clock is 1, Qn plus 1 is the I1. Okay. And when clock bar is 1, that means clock is 0. And when clock is 0, Qn plus 1 is simply I0. Any doubt? Shall we move forward? Yeah. So now, what is I1? So it is a D when it is applied to it is a D bar. When it is a D bar, here we are getting a D bar. Again we are getting. So it is there. Okay. So when clock bar is 0, we are getting a D. Initially here we are using the positive clock, so clock is 0, we are getting ID. Now here we are using a clock bar, so clock bar is 0, we are getting a D. Now when clock bar is 1, we are getting a I naught. What is I naught? Qn plus 1, it is go
Q.
there, so it is a Qn plus 1 here bar. Here we are getting a qn plus 1 bar. Again we apply on a buffer, so we are getting a qn plus 1. So if it is a day, we are getting the qn. Okay. So by changing the input or interchange input, we are using the clock. In place of clock, we are using the clock bar. Okay, now we go to the question. Here we are using the clock bar, D as a I1. Okay, clock bar and D as a I1. So this is what? Negative latch. And second circuit, sequential circuit, element 2 is positive edge. Okay, sequential circuit 1 is negative edge and sequential circuit, sorry, negative level, and sequential circuit 2 is the positive level. And when we cascade this particularly combination, what is this? It is a positive as triggered flip flop. Okay, so it is a positive as triggered flip flop. Now, if sequential element 1 is removed from the circuit in the figure 1, the remaining circuit will be one. So if we remove this sequential circuit, so this one is the positive level. Okay, second circuit is the positive level. So positive level, positive latch, or positive level. Okay, in the circuit of the figure 1, the input D, internal node QM, Q noise in the input node can disturb the internal state when clock is 0. Okay, yes, when clock is 0, circuit 1 it is a level triggered. Okay, so it is a negative level triggered, so negative level triggered is the clock. So if clock is 0, so that means the input we are applied at the input, we are getting similar as the output. Now, if input is affected with the noise, we are getting the same noise as the output. We are getting a same noise as a output. So it is a true state. The sampling edge of the sequential element 2 in the circuit in figure 1 is the sampling edge of the sequential element 2, where it will be start changing, okay, or basically on particularly what particularly point it will be separate. Okay, so before starting of the negative level, so before starting of the negative level is what? Falling edge. Okay, falling edge. So falling edge is just before apply the negative level. Okay, so that particular point is the point of sampling. After that, the data will be changed. After the data will be changed. Before that, there is a change in the data. Functioning, change in the functioning also. Okay, change in the functioning also. And after that, change in the functioning. So where the functioning will be changes when there is a falling edge. Similarly, if you are talking about the element 1, so it will be rising edge. It will be rising edge. Now setting setup time and hold time. Any idea? What is setup time and what is hold time? Yes, what is the setup time and what is the hold time? So if you see the diagram, if we draw the previous diagram also. So if you see the diagram, so this is my clock pulse. This is my clock. And if I represent my data D this way. Okay, this is my diagram. Why should I represent the diagram in this way? Is that till now we are not getting what is the final data. we are considering any situation. Maybe the data will be 1 or maybe the data will be 0. Okay? Or in this particularly, maybe the data is 0 or maybe the data is 1. Okay, so data should be anything. Data should be anything. So we have went till the data is not defined, we don't consider that the data is only the 1 or data is only the 0. So we analyze the behavior, either the data should be 0 or either the data should be 1. Okay? Now, if we are talking about the day when the data will be changed from 0 to 1. Okay? So before changing this one, this is called the setup time. Okay, this is called the setup time. And after finalizing the data should be 1, it will be the hold. The position will be hold, so it is called the hold time. Okay, the data will be start changing from 0 to 1. So we have to set up that data will be go from 0 to 1. So it is called the setup time, because we have to set up the data will be either go from 0 to 1 or from 1 to 0. Okay, so generally what we consider from where the data will be going increasing, we start increasing. After that, the data will be starting. So it is called the setup time. When the data will be approaching to the final value, after that time period, it is called the hold time period. Why? Because you have to hold the data for a longer distance. Okay, for a longer duration. So that's why it is called the hold time. So two types of timing are available. One is the setup time, second is the hold time. Now in between them, if anything will be happen, there is no effect in between this. Why? Because your data is not stable. Okay, your data is not stable. Like similarly, if any particular thing, like for example, if I am going to play, okay, before going to play, I have to set that I wear some clothes for my playing purpose. Okay, so basically, I set up that I will go and play any of the game. Okay, I will go ahead and play any of the games, but before that one, I have to set up. I talk with my parents. I just wear the dress that I can use in the for the playing purpose. I can wear shoes. Okay, so all particular things I have to do for going for playing with anything. Okay, so that particular time is called the setup time, because I set up myself for going playing for basically for playing purpose. Okay, now after that my setup will be done. I just move from this particularly place to my ground. Okay, and after approaching to the ground or basically any court or any ground, indoor or outdoor, I have to hold there. I have to stay there. It is not possible that when I go there and after that suddenly they will ask me that you can play. Okay, I have to stay there for some time. After that, they will recognize me that I am there. After that, they call me that you can also play. Okay, so with a simple example, I just relate this one with the setup time and hold time. Now, what is the difference between what is in between the setup and hold time? Like for example, I am going from my place to the any playground. Okay, and in between this one, mm, anything will be happen. Okay, anything will be happen. So this particularly thing will not affect either at my house. Maybe there is no electricity at my playing ground. There is no electricity. So anything will be done either on my house, either on my playground. There is no effect of that. Why? Because I am traveling between one position to another position. I am on bike. Okay, I am on bike. So particularly that is called the difference between the setup and hold time. So in between this one, there is no effect. Start with Hello. Yes. No, no. Okay, so basically the minimum time before rising edge is called the setup time. Okay, and minimum time after rising edge is the hold time. Now it is a basically DA and question number 6 to 9. One clock is given. We assume that there are no setup and hold constraint. Okay, that means setup and hold time both are same unless mentioned otherwise. What is the following data will be reached at QM? So first of all, what we see that QM. So QM is a negative latch, negative level latch. Okay, so if the clock is 1, no effect. But when the clock is 0, we transmit the data. So initially the data will be transmitted D1, then D2. Okay, after D2, D3 will be started, but D4 and D5. Okay, so data will be transmitted in this. So D1, D2. So which of the following data will reach QM? So initially the data will reach a QM as a D1. Then D2, then D3, then D4 and D5. Okay, no data will be lapsed because you see that when the negative latch will be start, negative level will start, D1 is the data. So D1 will be transmitted. D2 will be transmitted. Now, before starting the positive edge, D3 will be also started. Okay, so D3 will be transmitted. Now, for the positive edge, till that this point, D3 is remain constant. Okay, in the direction of positive edge, the D3 will remain constant. But when the negative will be started, D4 will be transmitted. This amount of data D4 will be transmitted. Then D5 will be transmitted. It will be remain constant till this point. Okay, so all data will be transmitted. Which of the following data will reach at Q? What is Q? Q is a positive. So I can do one thing is that I just copy this image. Okay, so this is the data. Now initially we are talking about this point. Okay, so this is so initially if you are talking about the QM, so before the positive edge, no data will be. So before the positive edge, we are considering the data will be no. Okay. When the negative will be started, the data will be deeper. Then data will be okay, and then data will be deeper. So D1 will started, D2 started, and D. Now for the positive edge, no changes. So till now there is no changes. Again negative edge. D4 will be started. Again D5 will be started. Okay, it will be constant up to this point. Okay, now Q. Now this is the data. Now it will be passed through this flow. So initially data is not configurable. The data will be remain as it is. Okay, when the again the next positive is D3 will be started. D3. Then D4 will be transmitted. We will remain constant at this point. After that, D5 will be transmitted. Okay. So only the D3, D4, and D5 will be transmitted. D1 and D2 will be lapsed. So if you are talking about the Q, so D3, D3, D4, and D5. Oh, sorry. Yeah. D3, then D3 will remain here with constant. Okay, D3 will remain constant. Because if you see that this is a D3, this is a completely D3. This point D3. Okay. Now after that D4 will be started, but it is a negative edge. It is a negative edge, so no changes. Okay. So D3 will be remain at this point. This is all D3. After that, this is all D5. Okay, so Q is only D3 and D5. Q is only D3 and D5. If there are the setup and hold constant for the flow case, which of the following data will have setup violations? Yes. Now, if you see that this is the data changes for 0 to D1. Now, this is the edge. Okay, this one is the edge. Before edge, this is the setup time, and this one is the hold. If data is vary from 0 to 1, data is vary from 0 to 1. So before 0, this is the setup time, and after it becomes 1, we are saying this is the hold time. The hold time is from the setup. Okay. Now, in between these two, in between setup and hold time, if any data is changes in this duration, if any data is changes in this duration, that particularly follows the violation of setup and hold time. Okay, that particularly violate. So if we see here, if you see here, now if you see, so setup violation. So this one, any data is changed. Here data is changed. Yes. 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 There are four setup time. Okay, there are four setup time. One is this one is this one is this one, and one is this one. Okay, so four setup time is there. Now, in which setup time will be considered on the positive rising. Okay, on the positive rising. So we can't consider this as a setup time. We can't consider this as a setup time. Any doubt? So how many setup time remaining? Only two.
Two.
Okay, one is this one is this one, and second is this one. Okay, now in which setup time the data will be changed?
First, D2
First
to
one,
D3.
D2 to D3. So if you say this is the first setup time, this is the second setup time. So in the second setup time, the data will be constant. But in the first setup time, the data will be changed from D2 to D3. So which one, which particularly violation? Here. So we can say that D3 or D2 will be a violation. Okay, because data will be changed as a D3, so D3 violation. Now, which of the following data will hold violations? So how many hold are there? Hold time is this one, this one. Now, which we consider as a hold time when the data is rising edge, when the clock is a rising edge. So first, this one is not a hold time. This one is not a hold time. Why? Because it is a falling edge. It is a falling edge. So we always consider the hold time for the rising edge. So two things are the particularly these two are the holding time. Now, if we are talking about this holding time, data is constant. Now, if we are talking about the D5, this holding time, the data is constant. So for this one, data is constant. For this one, data is constant. So that means no particularly hold time will do the hold violation. So if you see, then none. The circuit with input En and output Y is given below. The circuit heading. Okay. The output Y at time 320 T is equal to 60. Okay, so it will be taking the 130 nanosecond. So it will be taking the 130 nanosecond. 85. Okay. So So, so initially, if enable is 1, this becomes 0. Or we consider y also 1. Y is 1. Okay, so basically at t is equal to 0, at t is equal to 0, y is 1. Okay. We consider as a y as 0 also. Now, at t is equal to 130 nanosecond, if y is 1, so this one is 1, this one is 1, it becomes 0. So we are getting as a y1, y2, and y3. So when t is equal to 130 nanosecond, y1, y2, y3. So y1 is 0. And if we consider y as a 0, y as a 0, so y1, y2, y3, y1 is 1, okay. Y2 is 1, so y1 is 1, y2 is 0, y1 is 1. Yeah. At t is equal to 130 second, y1 is 1. Okay. If it is a 1, it becomes 0. It becomes one. So it becomes a 0, 1, 0. So at t is equal to 130 second, y1 is 0. At t is equal to 260 nanosecond, this y1 is, when t is equal to 390 nanosecond, y1 is 0. Now if t is equal to 130 second, y1 is 0, and then y2 is what? So y2 is 1
1.
at time period of, table in a more with respect to every time I want this table. with respect to every time I want this data. Okay, so let's we calculate for the y is equal to 0. Let's we calculate for y is equal to 0 at t is equal to 0 second. This becomes 0, this becomes 1. So we are getting as a 0 and 1 NAND. Okay, so we are getting that t is equal to 0, y1 is same 0. Now t is equal to 130 nanosecond. 1 and 0 becomes 1. So y1 is 1, y2 is what?
0,
Y2 is 0 and y3 is
1.
no. We are getting a okay. If we are getting y as a 0, consider y as a 0, t is equal to 0. So that means it becomes a 1 and it becomes a 0. Okay. So at 130 nanosecond, we are getting an output from because of this 10 is 1. Okay. But at this time, 85 nanosecond till 130 nanosecond, we are getting as a input or 0. After 130 nanosecond, we are getting 1 as input. But before 130 nanosecond, because this NAND gate will doesn't provide the input output as a before 130 nanosecond. So before 130 nanosecond, we are getting 0 as a input. After 130 nanosecond, we are getting 1 as a input. Is it clear? So t is equal to 130 nanosecond. Y1 is 1. This is the Y1 point. If it is a Y1, this 0 will be applied to this one. So y2 is 0, y2 is 1, and this 1 is applied on this particularly. So it is a y3 or y is also clear. Yes, any doubt? Please speak. Any doubt?
Please repeat again.
Okay. Uh, like for example, we are considering y is equal to 0. So this is 0. Okay. So what is the meaning of this 0? That here we are getting a 1. Here we are getting a 0. Okay. So this is the data at t is equal to 0. So I just mentioned t is equal to 0. Y is 0. So that means it becomes a 1. It becomes clear. Now at t is equal to 130 nanosecond. Enable is 1. This 0 is at this particularly point. So 10 output is 1. So t at 130 nanosecond, this output is 1. But the input of this one before 130 nanosecond is this 0. So this 0 is the input for this NOT gate. Okay, so we are getting a 1 here. Any doubt?
No, sir.
Okay, and this 1 is the input for this NOT gate. So we are getting a 0 here. Clear? After 85 nanosecond. So t is equal to 130 plus 85 is 215 seconds. the output is same. Why? Because it will be providing me the output after 260 seconds. 250, 260 nanosecond, because 130 nanosecond it will be providing me the output. After another 130 nanosecond, it will provide me the second output. Till that, the output is constant. Okay, till that output is constant. But after 85 minutes, after 85 nanosecond, this one will be applied as input of this one. So we are getting this 0 here. Okay, we are getting a 0 here, and this output will remain same 0. Why this remains same? Because this particularly 0 will be applied to this one after 85 nanosecond. Okay, now if we go, t is equal to 300 nanosecond, because we add a 185%. Now t is equal to 300 nanosecond, this 0, because of this 0 we are getting a 1 here. Okay, now this, because of this one, we apply the input at this point, so we are getting a 0 here. Now at this point we are getting 1 applied at, sorry, this 0 is applied, this 0 is applied, so we are getting a 1. Getting my point?
Yes, sir.
Now can I do this one in the one another way? If you are getting a problem, I will do it another way. 130, 85. Okay, at t is equal to 0. At this point, I am just representing as a q n plus 1 and 2. Okay, this is the q n plus 1 and 2. And this is the q n plus 1 and 2. Okay, now we consider the y is equal to 0. So what is the meaning of that? Qn is 0 at this point. Okay, here it is Qn is 1, and because of this one, here Qn is 0. Clear? Now after
Yes.
130 nanosecond, 130 nanosecond. So enable is 1, this is 0. What we are getting? So Qn plus 1 is 1. Qn plus 1 is 1 now. Okay, but this 1 will be applied to this inverter, and this inverter will be giving me the output after 85 nanosecond. So that means at t is equal to 215 nanosecond, this one will be going to the this inverter, and we are getting Qn as a 0. Okay, Qn plus 1 as a 0, and this particularly 0 will be applied to this inverter, but it will be giving me the output after 85 nanosecond. So at t is equal to 300 nanosecond, this 0 will be applied to this inverter, and we are getting Qn plus 1 as a 1. Any doubt? Any doubt? So after 130 nanosecond, we are getting a output as a 1 here. But output of this one is similar to the previous. Similar to the previous. Why similar to the previous? Because it will be changing the output after 85 nanosecond. After 85 nanosecond, when the data will be changed. Data will be changed after 130 nanosecond. So after 130 nanosecond, if we add a 85 more nanosecond, the data will be changed. But till that, my next state data will be similar to the previous state. And similarly for this one also, the next state data will be similar to the previous state. Clear? Now this particularly 130 nanosecond, it will be give me the data after 130, after 260, after 390, after plus 15520. Okay, so this will be giving me the data after every 130 nanosecond. So if we are changing the data after 130 nanoseconds, so next data will be available at 260 nanoseconds. So at 250 nanosecond, the data will be same. Okay, so data will be same. So if it is a qn plus 1 bar, so it becomes a qn, and the data will be same. So it is a remaining one. It will be remains one. Okay, here the data is changed. Here the data is changed. Okay, here the data is remains same. So qn plus 1 now the data will be same. After 260 nanosecond, okay, this data qn plus 1 data will be again going to the feedback, so data will be same. So here if we are getting the one. Okay, the rest data it will be remain same, and it will be remain same. Okay, at 300 nanosecond, this data will be remain same. This data also 250 to 300, 85 nanosecond data. That means the data at this point 250 nanosecond, it will be the inverse. So the data is same, but the data will be changed. Okay, now where the data is changed, data is not changed here. Now after t is equal to 390, after t is equal to 390, this one will be going as a input of this one. This one will be going as the input of this one. So this data is changed. The remaining data no changes because the previous data is not changed. So the remaining data is not. So what we are getting at t is equal to 320 picosecond. It is a y is equal to 130, 25, 250, 300. So after 320 nanosecond, the data of y is 1. Okay, after 320 nanosecond, the data y is 1. Okay. Now second, what they are asking as a 620. So we verify again. So 390 the data will be changed. It will be effect on p is equal to 390 plus 85 is 475. It becomes same. It becomes a 1 same. Again t is equal to, again we add a 85, so it is a 4 560. So the data is same. No, data is changed. It will be remain same, but this data will be changed, so it becomes a 0. So at 620 nanosecond, the data y is we are getting mistake. Okay, I think we have created table in a good way, so we get the answer. Please refer the below circuit diagram as figure 3 for question 11 and 12. This is the DEQ bar. The now the practice assignment is complete. If you have any other doubt, you can ask. Okay. So I think thank you all. If no doubts.